Mm, Let us wait for 1 or 2 minutes more. So, I guess. So, were you present in the last lecture? Susaretha, if I'm not pronouncing it incorrectly. Hello, am I audible? Would you please confirm if I'm audible? Okay, so did you attend the last lecture? I mean the last tutorial last Tuesday. Okay, fine. So since let's wait for 1 or 2 minutes since till the people are joining, could you please quickly introduce yourself? Like what are you currently pursuing? Oh, okay. So where are you working as an assistant professor? Could you please tell? I mean, it is fine. You can open your mic and chat. That is fine. Okay. I am hoping some more people will join. Okay, yeah, fine, no problem. So maybe at max we'll wait for 1 minute and then I'll start. Okay, so those whosoever have joined just now, have you attended the previous lecture? I mean, on the last Tuesday?
Yes, but I could not get chance to finish it. I have 15 to 20 more minutes left. So is it okay to continue here or should I be taking the recording section?
I did. So you did not cover the last 15-20 minutes?
Yes, yes.
That is fine. I mean, I
Oh,
might have covered some problems only. Initially,
mhm.
I already taught about the basics, so that will be enough.
Okay.
Yeah. So maybe we can start now. It's so maybe more participants will join later. So let us start. Welcome to the live session for the week 2 for the course Semiconductor Device Modeling and Simulation, which is taught by Professor Vivek Dikshit from IIT Kharagpur. And I am Anant Singhal, a PhD student from IIT Jodhpur, and I'll be assisting you in solving the assignment problems which are similar to the assignment problems that have been assigned to you for this particular week. And as you can see, this is the course outline. So in the previous week or the first week of this course, we discussed very briefly about the very basics, like what are the devices, why, what is this semi or the nanoelectronics that we are talking about, what is this device scaling, why we generally want a smaller and a smaller device, and then we see some of the basics of crystal unit cell and Miller indices, I mean some basic numericals, but the main gist was more towards what is basically semiconductor device modeling and simulation is. So let me quickly refresh. Said the modeling is nothing but the mathematical representation of a certain aspect. So before fabrication, we can actually simulate. By simulation, we mean that we can have a virtual fabrication or a virtual simulation of the device to see whether if the device will work in real world or not, and after that we can fabricate it. So that will help in basically saving a lot of resources also, and that will help in a lot of simulations or to obtain more amount of data also. So that is why the semiconductor device modeling is quite important with the semiconductor aspect. So in this particular week, like the as you can see, the topics are quite less. So I'll be again covering all the basics of these topics. So initially it is the reciprocal space. So we can go towards the numerical problems because it is not as much of a theoretical part, or it is not as much needed for the understanding. Then we'll be seeing what is doping and some of the band structures and how do they arise in a semiconductor. And at last we'll be talking about effective mass very briefly, and we'll maybe see some of the numericals if time permits. So let's quickly move ahead now. So in the last lecture we have already seen what is a crystal lattice, and we did some of the numerical related to. So basically, first of all, we already know that silicon is a single crystal silicon. So what we have is we have certain orientations that are periodic in nature, and we did some of the numericals based upon FCC, BCC, and diamond cubic numericals. So this is basically the structure of the silicon. And so these all numericals are covered in perspective of direct lattice. By direct, I mean the direct formation of the cube. So let's say this is, I'm giving a very raw example. So let's say this is maybe BCC because it is easier to draw. So BCC, what we have is all 8 atoms at the corner. I hope you are already aware, and one at the middle. So this is the direct lattice. I mean the atoms that are present directly into the silicon lattice. So there is one more representation which is called as reciprocal lattice. So first of all, why do we even need reciprocal lattice? Because it basically provides a very simple formulation. So it is done using Fourier transforms only. So since we need to know the properties of material, so we do some diffraction techniques or some techniques to get aware that what is a wavelength or what is the criteria of or the dielectric of the device. So to get the easier formulation, we in general prefer reciprocal lattice. So this is achieved using Fourier transform of the direct lattice. And as I am talking about the Fourier transform, so it generally it is done in the frequency domain. Let's take some of the basic examples. I mean that will cover the most of the basic of this particular topic. So first of all, let's start with the direct lattice. So it says what is the ratio of the FCC primitive unit cell volume to the volume of the BCC primitive unit cell. So assume that the lattice constant is A. So both of them have a lattice constant A. So let's quickly move towards it. I mean this is quite easy. So first of all, it is very important to know that the number of atoms that we have in a primitive cell is always 1. So a primitive cell always contain a single atom, and we have already, so here it is asking for FCC and the BCC ratio. So for let's say for FCC, the number of atoms in a unit cell. So this is what we already discussed last week. So can someone quickly tell what is the number of atoms that are present in a number in a FCC based structure?
4.
Yeah. So why 4? Because we have 8 atoms at the corner and we have 6 atoms at each of the faces. So each of the atoms contributing half for the face and 1/8 for the every corner. So this will give us 4 atoms. And similarly for BCC, if I can write quickly, it is 2. Yeah. So BCC why 2? Because we have atoms at the corner and one is at the middle or the body center. So we have 2 atoms. I mean, this will give you a very generic idea. So we have already seen. So if I write, and we know that both of them are solid cubes, so the volume will be A cube only. And since both of them have a lattice constant of A also, so that is why I have written. So volume of a primitive cell now if I write for FCG. Now since the primitive cell can only contain a single atom, so we need to divide the volume by the number of atoms that are present. So for FCC it is 4. And similarly, the volume of a primitive cell in case of a BCC is A cube by 2 because we have 2 atoms in a unit cell. So now the question is asking about the ratio of FCC to BCC. So I'm denoting it as FCC, the VFCC, and this is VBCC. And let's write primitive. So it will be nothing but A cube by 4 divided by A cube by 2. This will give us 1 by 2. I mean, this was a very basic problem, and the correct answer would be option A. I hope this is clear. I mean, this is very generic. So if you have any doubt, you can ask right away. I'll be covering the reciprocal space in the next problem, so that will give you a more better idea about that. So shall we proceed?
Yes.
Okay.
Yes, sir.
Yeah, so now we have a problem which is related to, I guess, the reciprocal, right? Yeah. So the problem states that what is the volume of the primitive unit cell? So volume of the primitive unit cell, again, we need to focus on each and every word, of the reciprocal lattice. So it is asking for the reciprocal lattice volume of the FCC, and assume that the lattice constant of direct lattice. So we have given the value of A as 5 nanometer, and the solution is in centimeter, so we can write this as 5 times 10 raised to the power minus 7 centimeter. So we'll use this A later. Let's first calculate a generic value. So as we have already discussed in the previous problem, so the FCC direct lattice, so the volume of FCC direct lattice, if I talk primitive only, it is A cube by 4. I mean, this is what we already know from the previous problem. So now to calculate volume in the reciprocal lattice. So we have certain constraints. So first of all, this is FCC. So we have atoms at each and every face. So these three, let's say, are on the faces and we have corners. So I'm only drawing the three front faces to make it clear. So to calculate the reciprocal space, we need to calculate the minimum distance. I mean, we first need to see the nearest neighbor atoms for a particular crystal from a particular atom. So let's say, I mean, let's take some directions also. Let's say this is X, this is Y, and this is Z. So for this, the closest atom will be in the X direction will be this face, and which is basically, and in the Y direction, or in the let's say XZ plane, it is this atom, and in the YZ plane it is this atom. So we'll quickly do the, okay, wait again. Yeah, so we'll quickly do the volume analysis. Let's say these three vectors are namely A1, A2, A3. So the volume, we know that it is the dot product times the cross product of any two vectors if we are calculating in a 3D vector space. So this is what we ultimately need to calculate for this particular problem. And so we'll be going one by one. First of all, we need to calculate what is A1. So let's say A1 is in the X axis. So let's say this is A1. So you can see A1 will be in the YZ plane, not this one. Let's say this is A1 because it is 0 in the X plane. So are you able to understand it is X equals to 0 in this particular plane? Is there any doubt in this? Please let me know if you have any doubts, because it needs to be clear. Okay.
No doubts. Yeah.
Okay. So we know that we have the side of each and every cube as A. So if I calculate the distance, uh, let's say in the Y plane, which is this plane, so maybe I can draw atom here. So this is the direction distance for the Y plane. So if this complete distance is A, so this will be A by 2, the half the distance. So if I try to write A1 as in the vector form, so it will be A by 2 Y cap, and similarly in the Z plane, which is the inside plane, it is again A by 2. So if I calculate from here to here, this is A by 2. So it is A by 2 Z cap. Sorry. Yeah. Similarly, we can write A2 and A3. So A2, let's say it is in the Y plane. So I can write A2 as A by 2. So I can write Y as A by 2, and this is X plus Z. And similarly A3, which is, let's say, in the Z plane. So I can write it as A by 2 X plus Y. Is it clear till here? I mean, this is direct. So
Yeah.
yeah, great. So we can now calculate the volume of a primitive FCC in reciprocal space. So I'm just doing a single derivation, I mean, to just familiarize you. Rest we can do the direct formulas also, using direct formulas also. So it is a1 dot a2 cross a3. So a2 cross a3 we need to find once. So it is x, y, z. I am hoping you already know how to calculate the cross product and all. So it will be, sorry, so a2 is this. So it is 0 in y. So it will be a by 2, 0, a by 2. And a3 is this, which is 0 in z. So it is a by 2, a by 2, 0. So x cap we have uh, minus a square by 4 plus, sorry, not plus, minus y cap we have again minus a square by 4, and plus z cap we have a square by 4. So let me quickly tell you I have done it. So for x cap I have like neglected these row, and this multiplied by this is the thing. So 0 multiplied by a square by 4, or a by 2 times a by 2. So that is how I have written it. So if I take common a square by 4, this is minus x cap plus y cap plus z cap. And yeah, so volume will be, only writing volume. So it is a1 dot a2 cross a3. So a1 if we see in, yeah, so it is a by 2 times y plus z. And the dot product of this is a square by 4 times minus x plus y plus z. So can someone quickly tell how to do the dot product of this thing? I mean, this is very easy, but still, can someone tell? I can keep a cube by 8 separately, and then y plus z times minus x cap plus y cap plus z cap. So dot product to any perpendicular direction is always 0. So we need to only compute y times y and z times z. So if I do that, what I'll get is a cube by 8. So this is 1 plus 1, which is 2a cube by 8, and ultimately it is a cube by 4, which is equals to also the direct space volume, right? Direct lattice volume. So for the case of this FCC, the direct lattice volume is equals to the case for the reciprocal lattice volume. I hope it makes sense. Sorry, press something. Okay, I somehow left the meeting. Am I audible now?
Yes, yes.
Yeah, yeah, okay, yeah, great. So we have this as a reciprocal volume. So what we can do is we can calculate it quickly now. Okay, sorry. So this is the volume we have. Now we need to calculate the reciprocal lattice. My apologies. So I was calculating the volume of primitive FCC initially. So for the reciprocal lattice, what we need to have is, so that was for the case of for a direct lattice. So now we'll calculate for reciprocal lattice. Let me repeat. I was calculating it for the direct lattice, not the reciprocal. So for the reciprocal lattice, we have three perpendicular vectors. Let me write them. So one is b1, which is nothing but 2 pi times a2 cross a3 upon the volume of the direct lattice, so which is this only basically. The second vector is b2, which is 2 pi a2 or a2 is already there, so a3 cross a1 by v, and b3 is 2 pi a1 cross a2 by v, and v is again the same, and the final volume will be b1 dot b2 cross b3. So let's quickly do the calculations. I mean, this is straightforward, but yeah, it takes some time. So let's first calculate b1. So b1 is nothing but 2 pi. I guess we already have a2 cross a3, so I can use that. The volume I can write quickly as a cube by 4, and a2 cross a3 we did calculate or not. Yeah, a2 cross a3 is this. So I'm writing this a square by 4, and we have minus x plus y plus z. So this is what we have b1. Maybe we can have some simplification. So this 4 will get cancelled out. So it will be 2 pi by a, and we have minus x plus y plus z. Similarly, b2 will be 2 pi a3 cross a1, and this is again a cube by 4. So let's quickly do, okay, let's do it once only because we'll not do it again. So a3 cross a1 is x y z. I write again a3. What do we have as a3? A3 is this, a by 2, and then xz. Okay. Oh, sorry, it is yz. Uh, 3 is xy. Okay. So a by 2 0, and the first is, sorry, a by 2 yz. So if I quickly calculate this, this will be a square by 4. I'm writing directly. This is minus y cap and plus z cap. So this will be b2. Sorry, this is vectors only. And if you calculate b3, so you see there is a minus sign here, this shifted here. So b3 will be something like this, x cap plus y cap minus z cap. Is it fine with everyone? Any doubts here? These all are just mathematics. Any doubts?
No.
Great. So we'll calculate now the volume of reciprocal lattice. So I'm writing RL, so which was B1 dot B2 cross B3. So B1 is this thing. So I'm writing here 2 pi by A, and x, I guess it is what? Minus x, okay. Minus x plus y plus z cap, and B2 cross B3. So we now need to do the cross product of these two also. So, okay, let me write here only. Sorry, yeah, x, y, z. So I'm taking a square by 4 common from this and a square by 4 common from this, and this will be, did I do something wrong or what? Okay, so we have this multiplication also in this, so again 4 and 4 will cancel out, so this will be 2 pi by a in both the cases. I hope you're able to understand. So this will be 2 pi by a because this is the constant factor for both. Is it fine?
Yes, yes.
Yeah, yeah,
We
yeah.
are getting that.
So 2 pi by a cross 2 pi by a, this is the scalar terms, so I'm keeping them out. This is now b2 cross b3, so 1 minus 1 1 and 1 1 minus 1. Okay, yeah. So if we calculate it, this will be 1 minus 2, sorry, 1 minus 1, so this will be 0, I guess. So x term will be 0. So 2 pi by a cube, I'm writing minus x plus y plus z, and the x term will be 0, the y term will be minus 1, so it will be, I'm not wrong, it will be 2 minus 1, it will be 2 y cap, and the z term will be 1 plus 1, yeah, plus 2 z cap. So now we only need to do the calculation for y and z, so it will be 2 plus 2, that is 4. So 2 pi by a cube, and this is 4, and this will give me 2 8 3 32, I guess 32 pi cube by a cube. I guess this is the exact formula. So is it clear, all the mathematics? Any doubts? You can quickly ask here only, because this is the only problem will I'll be showing the derivation for this. So yeah, this is for FCC, the volume of reciprocal lattice, and the volume of reciprocal lattice for BCC is also calculated similarly, and it is, I guess, let let's see it in the next problem. I mean, it is 16 pi cube by a cube only. So now the problem is, what is the volume of a primitive unit cell for FCC if A is this? So we already know now. We have just calculated the volume of primitive cell in reciprocal space is 32 pi cube by a cube. We have the value of A, so let me know the answer quickly so that we can move ahead. Until you are also calculating the answer, can someone please float a WhatsApp group link that will help for coordination of all the lectures? So please let me know if someone is doing it till then. I'm requesting, can someone do it right now? They can float the link in the chat box. Okay. Do I need to choose, or is someone volunteering by himself or herself? Um, okay. So Satvik, can you do this? Uh, I hope not. Ravika, can you do it? Okay, again, I hope not. So I'm quickly sharing my phone number. So please, someone send me a link. Yes, who is this?
Are you talking about the sum or the WhatsApp group?
I'm talking about the WhatsApp group. So,
Oh, I'm not aware of it. I'm sorry.
okay, how to make a group? You're not aware?
Oh, okay. I do not have numbers. How do I make it?
I mean, you can just add one participant, and
Okay.
then there will be a group link that you can share in the chat box. So I've shared my contact
Okay.
number in the chat
I'll
box.
I'll do it. Yeah, yeah. Give me a minute.
Sure, sure, yeah. Till then, please everyone try to get the answer. I mean, this is a calculation now. So 32 pi cube by a cube. So volume is 32 pi cube by a cube is 32 times 3.14159 something cube by 5 10 raised to the minus 7, because we need to do it in centimeter. So volume in direct space is in centimeter cube, but in reciprocal space it is per centimeter cube. So the final answer will be in per centimeter cube. Sorry, this is cube. So let me also try to calculate. This is okay, pi cube times 32 divided by 125. So I'm getting 7.937 times 10 raised to the minus 7 sorry, not minus, plus 21. Oh, it is minus. Mm, yeah, I mean, there might be some problem with plus minus, but 7.937. So option A would be the correct answer. It should be plus, no? A is in the denominator, and A is, yeah, it should be plus, most probably. I'll check once if it is plus or minus, But yeah, it is something 7.94 times 10 raised to power 21 or minus 21. Any doubts in this? Yeah, if not, you can quickly let me know the answer to this. Okay, yeah, thanks. So please, everyone, please join this group. So Ravika has shared a group invite link on the chat box. You can just click it and you'll be able to join the group. So in this, I'll be posting some of the reminders for all the lectures, and if you have any queries, you can ask over WhatsApp. That would be a quicker response.
One question is that all these solution what we're doing now.
Yes. Okay, I lost you. I'm not able to hear now. Is it the case with everyone?
I was saying that all these calculations or this problem solving thing, do we get this whatever we're doing it as it is as a PDF or something?
Yes, yes.
Yeah.
So,
Okay.
so NPTEL might have shared you a drive link, right? No?
Yeah, I'll check that.
Yeah. So
Okay.
the first week is already uploaded, and just after the class, I in general upload these as a PDF.
Okay. Okay. Thank you.
Yeah. So I'll request again to join the link that she has shared with everyone so that we can have a group. Yeah. So the next problem is we can ignore this A is equals to. So we need to again calculate the primitive unit cell reciprocal relative for BCC now. So I'm just telling you directly is that after all that derivation, it will come out to be this 16 pi q by q. You can do all these things again for the BCC. The only difference will be it will be a cube by 2. So that is why the only difference will come out to be by 2 of this thing, and that will be 16 pi cube by cube. And I'm not repeating it again. Is it fine with everyone? Okay, great. So let's move ahead now. Yeah, it is recording, right? Yeah. Hmm. So maybe like before going to next particular problem, so there are some topics that I'd like to cover, like to explain you how this band structure come into existence and what is this doping and all. So if you have attended the previous lecture, we ended it with something called as Bohr's model, in which we have certain discrete energy levels that we have, uh, in which the topmost are the valence band electrons, and since they are very far away from the nucleus, so they are most likely to have the energy transfer, and only the valence band basically takes part in the exchange of energy. So that is what we have already established in the previous lecture. After that, we have certain theories that will help you in like getting some idea of why these bands are coming into the picture for a semiconductor. So let's do that quickly. So if I talk about in very conventional way, so we have three types of chemical bond. I mean, you might have already read them in your class plus one or plus two. So we have a thing called as, let's say, first I'll divide it into two parts. One is a primary bond and one is a secondary bond. So primary bond are generally which are interatomic. Like the bonds between the atoms and secondary are basically which are intermolecular. So in semiconductor we only deals with this primary bonds. We will not even be talking about these secondary bonds because first of all they have this thing called as van der Waals force of attraction, and in semiconductor we do require a certain force that can make the bonds or that can bond the two different even materials or different atoms. So we'll be only considering the primary bond for this particular thing. They have a thing called as electrostatic force to have the attraction, and the second is they are very strong and stable. That is what we need. And again they are classified into three parts. The first is ionic, second is covalent, the third is metallic. So this is like very basic, you have already read in your class plus one plus two. So why I'm telling you this is because this is how the band diagrams or the different band, uh, what to say is different bands of energy comes into existence. So if I talk in terms of ionic, I mean we have already know a very popular example, Na plus Cl minus will give you NaCl. Why? Because we have a strong dependence, or this Na plus ion needs a electron to completely fill its valence band or the valence orbital, if I say in terms of orbital, and this chlorine has an extra electron to give it to this donor. So this is why these ionic bonds are very strong. I mean, I'm just telling you a very basic of it. The most we are interested in is in this covalent bond. So covalent bond are in general made or formed by the sharing of electrons. So let me make, if you have heard of this H2, so this H we know it is 1s1, right? And let's say H2 is 2. So if this, I can make it something like this. So 1s1 is H and 1s1 is this. So to complete this orbital, we know it can accommodate 2. So it will be shared. So this, they both will be sharing these electrons to form a molecule known as H2. So these types of bonds are known as covalent bonds. This is what we generally comes into the picture for the semiconductors, and this all comes under molecular orbital theory. So what we have, again let's consider this H2 only, H bond H. So what we have a single atom for 1s, we have a single atom for 1s. So once they come into picture, they share something like this. So this is what we call as bonding molecular orbital, and we denote it as sigma 1s. Again we have 1s 1s, so what we have is a anti-bonding orbital also. So this is sigma star 1s. Sorry, sigma star 1s. Yeah, so basically these are the two bonding or the orbitals that are being formed once we have two hydrogen atoms which are coming closer to each other. So what happens? So as they are approaching towards each other, let's say they are approaching towards each other, there is there are two molecular orbitals that are formed. One is the bonding molecular orbital, which is denoted by sigma 1s, and one is the anti-bonding. So one is formed due to the attraction and one is formed due to the repulsion. So we have these electrons, so they will repel. So the repulsion will create an anti-bonding molecular orbital, and the attraction. So we have a nucleus. So nucleus will attract the electron that are present in the valence band. So that will create the bonding molecular orbital. And if I try to make in terms of the exact bonding molecular, so let's say this is atomic orbital. So I mean you must have seen these type of diagrams. So we have one electron here and one electron here. So this is 1s1, this is 1s1. So they are basically dividing into two. So this is how it looks like. So this is the bonding molecular orbital and this is the anti-bonding. And for a stable bonding, this is a criteria that the number of electrons in the bonding orbital should always be greater than that of number of atoms in anti-bonding molecular orbital. So this is what is molecular orbital theory is. And what we can say is we can conclude that when a number of atoms are coming closer to each other like this, So what happens when they are coming closer to each other, they are trying to form a systems, and we have discrete energy levels. So this is one energy level and this is two, and discrete energy levels splits into a number of energy levels, forming a band of energy. So if you have seen, so if we make a diagram, uh, in the energy in the y-axis and the interatomic distance, let's say I'm denoting it with a in the x-axis. So up to a certain point, what will happen, we will have a single energy level, and after that we will have a formation of the bands as I have made there. So there will be a lot of bands. So this is how these bands come into the picture, and this is all uh, being governed by the Pauli's exclusion principle that you have already read in your class 1, class plus 1 and plus 2. So can anyone tell what is this Pauli's exclusion principle is? Any idea? Okay, so basically what Pauli's exclusion principle is, it states that the joining of atoms to form a system, as I said, so it is kind of a system that we have formed using MOT, using the molecular orbital theory, that after joining a system, no two electrons can have a same quantum state or a same quantum numbers. So that is why we have a split of discrete energy levels here also. So basically Pauli's exclusion principle states that no two electrons can have a same quantum number. So that is why we have a split of energy in order so that electron can easily occupy a distinct quantum state. So I'm not writing what is Pauli's exclusion principle. I hope you have already have the idea. So if you have the idea, let's now quickly see what is happening in this silicon. So let me write it as formation of energy bands. Let's say we are considering a silicon only, which is 1s2, 2s2, 2p6, 3s2, and then we have 3p2. This is the valence orbit, right? So what we have is we have 2n electrons, that is 2n states from this, and again we have n 3p energy also, which is total, in total we have 6n states, right? P can occupy 6, and we have 2n electrons inside this. Here we have 2 n states, and already we have 2n electrons in this 3s2. So the total energy, if I can write, it could be 2n plus 6n. We have first of all 8n states, out of which 4 are occupied, right? So as I said, ionic is the most strongest and metallic is the weakest. So we have something called covalent bond in between, which are forming for silicon. And if I now try to make an exact band diagram, I mean, my drawing could be bad, but let me try to explain you what exactly is happening. So this is interatomic distance A, and this is energy. Let's say this is 3s2, this is 3p2, something like that. So what we have is, as we are going towards, as the interatomic distance is decreasing, so what we achieve is, maybe I can change the color of the pen. So what we see in general is this energy starts to increase, then we have a certain phenomena. Let me draw it first, sorry, not like this, and yeah, something like this is the case. So as we go towards or a lesser interatomic distance, so you can see here we have a large gap in between the two different energy states. So since we have a large gap, we don't have any energy. So this is what corresponds to the metallic bond. So here you can see, if I make a line here, so we have a difference in energy gap which is quite less. I mean, it is quite comparable, or it is in terms of uh, let's say few orders that can be seen by the naked eye. So here what you can see, we don't have any states, but here on the top we have 4n states, and in the bottom we have 4n states. So this is for covalent or for the semiconductors. And if we go more far away, then we have ionic bonding, and this Eg will increase more and more. So here I can write somewhere as ionic bonding also. But we are more interested in this covalent bond. So if I try to make some vertical lines, so yeah, let's try to do that. So this is still here, this is still here, this is still here, and this is still here. So you see we have different number of states. So if I try to draw a lot of lines in between, then we have some energy gap in between. In that we don't have any state, and then again we have foreign states in this. So this particular thing is what we call as valence band. This particular thing is what we call as conduction band, and the difference between these two bands is known as forbidden energy band gap. So in general, what we have is energy band diagram of a real semiconductor. If we say it is not, or it cannot be represented as a flat line, but there are certain energy states also available in the forbidden energy band gap, because you see if we move towards closer towards the atomic distance, there could be some states available in between them. So for just simplicity or for some practical reasons, what we do is we represent it something like this. This is what you see in your books, ECEV, and this is EG. So practically it is like this, but for simplicity, what we have is position, energy, and something like this. So this is the top of the valence band. This is the what to say, the bottom of the conduction band, and the difference between the energy is the forbidden energy band gap. So this is how bond formation happens, and this is how and this happens due to the discrete energy levels. Does it make sense?
Uh, Anant, can you explain what does A represent? You said interatomic
Yeah, yeah.
distance between two atoms. I
Yes,
came
yes,
late to
yes.
the class. Sorry. Yeah.
No problem. So basically, let's say this is a silicon and this is a silicon. So this is the nucleus, this is a nucleus. So this is a. So once they are coming closer and closer, they are forming or they are dividing into the discrete energy levels, as I told in the molecular orbital theory. So as they go more and more closer, they will form more discrete energy levels. So that is what just I try to explain you the significance, that if we have a smaller A, then we have more partition or the more formation of the discrete energy levels. And something in between is what we need or what we get from the semiconductors. Make sense?
Yeah, yeah, got it. Thank you.
Yeah. So yeah, this is how first of all band formation takes place, and this is how our real band structures. And this is what you will see in the whole course. We'll only be making the bottom of the conduction band and the what to say, the top of the valence band, and the band gap between those, or the energy gap between these, is the forbidden energy band gap. And this is how we classify the materials. I mean, again, I need to go to very basics. So we have now three materials. One is called as insulators, one is semiconductors, and one is conductors. So they can be now classified on the basis of this band gap only. So if we have a very high band gap, let's say if I classify which is greater than 3.5 electron volts, we in general call them insulators, and they are not conducting. I'll tell you how or why they are not conducting. And if we have the energy band gap which is close to, let's say, 1 electron volts, these are called semiconductors. And if we have no band gap, or if the conduction band and valence band overlaps, this is what is conductors, and they are always conducting, and they do not even need any additional energy to have some conduction. So why the insulators are not conducting? Because they require a huge amount of energy. So here you see in the valence band we have all the filled states. I mean, here I showed you, I guess. Yeah, in the valence band it is completely filled. So to have some free electrons, you need to provide certain energy to go this, so that this electron can go from here to here. Then only it will get free, and the flow of electron is current. So there is no flowing of electron in the valence band, and there is a huge amount of energy that is needed for an insulator. So that is why they are non-conducting, because we could not provide this huge amount of energy. Whereas a semiconductor can be conducting, so they are partially conducting, as the name suggests, semiconductors. So if you provide a certain amount of energy such that the electrons from the valence band goes to the conduction band, So that can basically result into the formation or the formation no, but the production of the current. So that is why they are partially conducting, and that is why we are calling them as semiconductors. So we have the control to make them as an insulator, or we have the control to make them work as a conductor. I mean, this is a very basic classification. So is it clear?
Yes.
Yes.
Yeah. So again, a very basic part. I mean, I know it can be boring, but this will help you in further classes also. If you have this basic understanding, then there is nothing that you could not understand, you or you cannot understand in the further classes. So let me cover this aspect for this particular lecture. So in general, semiconductors are class 3 to 5 semiconductor elements, in which we have, I mean, you have seen this periodic table, which is BALC, then C, carbon, silicon, germanium, and this is NPAS. So in general, what we use is these two. So class 3 to 5, we have these types of material, and these materials are having a narrow energy band gap, again I'm saying, and they have a electrical conductivity which is greater than that of insulator but lesser than that of a conductor. So before this, I mean, before this means 1 and 2, I mean, I don't remember, but it is, I guess, hydrogen, helium, lithium, then we have Na, something something like that, and here we have beryllium, magnesium. So these all are metals. And after this, let's say class group 7 8, uh, again oxygen, sulfur, something something, and then we have fluorine, chlorine, bromine. So these are all, if I try it, so these are all insulators, these are all metals, and in between we have the semiconductors. And class, sorry, this is 5 6 7. In class 8 we have all the inert gases, so they are not coming into the picture, so they are completely inert. So this is what we will be dealing in this course. We have certain semiconductors which can be pure, which are basically class 4. They can be have some impurities, which are basically class 3 to 5 semiconductors. And again, semiconductors are classified into a lot of things, but let's go towards the basic. I'm not going towards into it so much. Let me directly talk about the intrinsic semiconductor. So do already anybody already know what is this thing intrinsic semiconductor is? Some of you might have the idea.
It's just a pure semiconductor without impurities.
Yes. So without impurities, as she said. So the pure form of semiconductor is what we call as intrinsic semiconductor. So what I mean is, or what she mean is, hmm, so let's say we have a lot of silicons. As I said, these are all covalent bonds. So I'm making periodic structure. So we have 4 valence electrons in the silicon, and all of them have something like that. This only. I mean, let's only try to cover the basics. Or so these two will be sharing this, these two will be sharing this, these two will be sharing this, and these two will be sharing this. And this is how it is periodic. There is no exchange of electrons. So let's say I'm initially talking about at 0 Kelvin. So what we can say is valence band electrons. Maybe let me make it, sorry, yeah. So let's say this is conduction band, this is valence band. So valence band, as you can see, is completely filled in this. So valence band electrons are not capable of taking any energy, because I am talking about 0 Kelvin, so there will be no thermal excitation also. So it is completely filled and it is completely empty. So first of all, if there would have been any electron in this conduction band, right, so there will be free electrons, and that will be from that way will be able to generate some current, because flow of electron is current. But since we are talking about 0 Kelvin, so it is not possible. So first of all, if there are any electrons in this conduction band, they would have been called free electrons, because they are free to move. But in the valence band, we don't have any vacant space, so there are no electrons moving and there is no conduction. Uh, yeah, so this is the very basic. And if the valence band electron can reach to conduction band, and they can only reach if they are supplied some energy which is equal to or greater than that of this forbidden energy band gap. And it can be thermal, it can be optical or something like that. But what is the main thing? At 0 Kelvin you can see there is no thermal energy available, there is no energy. So at 0 Kelvin intrinsic semiconductor behave like a pure, can someone tell?
It acts as an insulator.
Yeah. So at 0 Kelvin it will act as a pure insulator because there is no conduction and there is no possibility of any conduction. But if I make it similar to, let's say, it's 300 or room temperature, so what could happen? Now what we have done is we have given it some excitation or some thermal energy. So at any temperature, first of all, the number of electrons, free electrons, is equal to the number of holes, and it is equal to the intrinsic carrier concentration. So n is the number of electrons or the free electron, as I said, this free electrons. P is a hole concentration, so I'll tell you what is hole concentration, and Ni is the intrinsic carrier concentration. So at room temperature, few of the electrons in the valence band may acquire sufficient thermal energy because we have fed some temperature, because of which the covalent bonds that we are talking about, these bonds may get broken. So once they get broken, let's say this is broken, so what we have is now free electron moving somewhere. So let's say I'm denoting it like this. So once we have this free electron, so whenever this electron moves to the conduction band, it becomes a free electron, and the deficiency of this electron, so let's say, again I need to change the color. What's happening? Hmm. So let's say we have these many electrons, and one electron went from here to here. So it was but basically here. So there is a deficiency of this electron created in the valence band. So this is what is hole is. So it is actually not a particle, but we call a deficiency of this particular atom as a hole. Please don't get confused. Hole is never a particle. Hole is just the deficiency which is created by the electrons which are going from valence to conduction band. So this is hole, which is basically we give it a name or mass equivalent to of that of a electron. And yeah, it has all the properties same, but it is only the positive charge equivalent of electron. So at any temperature, the electron concentration will be equals to the hole concentration, which is equals to the intrinsic carrier concentration. So this is the very basic. And yeah, I mean, if you have any doubts still here, you can ask, otherwise we can move ahead. Any doubts till now?
No.
Yeah. So there is one more concept. So as you see, there are a lot of free electrons, or sorry, not free, but the lot of electrons present in the valence band. So there is a possibility that these two guys can interact, and this process is what we call as recombination. I mean, this is one of more of the technical term I missed, so I'm just telling you this. I hope it is clear. So now what we have is the second class, which is known as extrinsic semiconductors. As someone already said that the intrinsic semiconductor is a pure form of semiconductors, whereas to have some more conductivity we add some kind of a impurity in that, which is what we call as extrinsic semiconductors. So till now what we have established is at room temperature the intrinsic semiconductor has a very small conductivity. As you see, it is only obligated to the thermal energy, so it is less useful. But what we can do is most of the electronic device for a semiconductor, let's say, if we add some small amount of impurity, it can have, or by deliberating added, I'm saying that we are deliberately adding some of the impurities in a semiconductor. So this thing, deliberately adding impurity in a semiconductor, can someone tell what is this?
Doping with other elements like.
Yeah, so this is what is called as doping. So this is the second topic, so I need to teach a lot to come here. I guess this, yeah. So doping is adding a impurity deliberately into a pure semiconductor to increase it, to increase the conductivity. So I mean, now you might have gotten some idea that how the electrons is moving from valence to conduction and how this doping will help. So if we add a certain impurity, let's say n-type impurity, let me give you a very quick idea. So n-type, we see, let's say phosphorus. So phosphorus is an n-type impurity, and what it has is it has an additional electron, 5 electrons in the valence band. And if we have a lot of silicons in presence, so silicons, we know that it is 4 valence, so this will be shared by this will be shared by this. So what we are left with, we are left with a free electron, right? So this is what will create the conduction into extrinsic semiconductor in compared to a intrinsic semiconductor. Similarly, if we have a boron type of impurity, we will have a free hole, because boron only have 3 electrons in its valence band. So silicon might be able to donate one of its electron to the boron, and that will create, or that will basically result in the creation of a hole. Any doubts still here? I mean, these all are basics. I guess I have covered a lot, and this is what doping is. Yes, any doubts?
No, no.
Yeah, okay. And as I said, this is applicable for anywhere, and there is a thing called mass action law, which says that the np is always times equals to ni square. So yeah, this is it for the theory part. Maybe we can try to do some numericals now. So you can try this. This is very basic. So in a silicon crystal which is doped with this arsenic. So arsenic is what? Which type of impurity, I mean? Uh, any idea? I mean, I have already.
N-type.
Yes. So we have a single crystal silicon which is doped with the n-type impurity. So it is a n-type extrinsic semiconductor basically. It is given that what is the concentration, what is the equilibrium hole concentration, it is asking. So yeah, you can, I mean, this is np is ni square. So quickly let me know the answer. Maybe you can take 1 minute because it is very easy.
2.25.
So I've already got one answer. So let's see. N is 10 is per 15 times p is what we need to find, and we have ni square which is 2.25 times 10 is per 10 or 20. So P will be 2.25 times 10 raised by 5 per centimeter cube. So yeah, option C is correct. So again, we have a similar problem. So we have a single crystal silicon which is doped by a donor impurity. So donor is N type and acceptor is P type. So we also denote this by ND, and we also denote it by NA just for future reference. And Ni is given. So this is again very easy. So ND is already given. So since it is a N type of semiconductor, so N will be equals to ND, and P will be equals to Ni square by N, that is Ni square by ND. So first is already 10 raised by 13, second will be 7. So option B will be the correct answer. If you have any doubts, you can ask. Any doubts? Anyone?
No, no.
Okay, so we can quickly move forward then. Yeah, so this is a good question. I mean, this is theoretical, but it will judge your understanding. So maybe you can type your answers in the chat box. Take 2 minutes to think, and let me know what do you think the answer would be. And also please join the WhatsApp group, those whosoever have not joined. Maybe you can share the link once again some of them have uh, joined late.
Yeah, sure.
Any answer? I mean, this is quite straightforward if you have understood.
Option B.
Option
B.
B. Okay. Yeah. Anyone else? Could you tell me the reason why did you choose option B?
Because gallium is P type
Okay.
and arsenic is N type. So it is this hetero compound semiconductor.
Hmm.
So here the gallium is acting as P type and arsenic is acting as N type. If it is replaced, silicon is replaced by those atoms. So silicon at the place of gallium will act as P type. Yep. And N type at arsenic. Is it right?
Yeah, yeah, we'll see, we'll see. Don't
Okay.
worry. So let me. So as he already said that gallium is what is it? Yeah. So as he already said, gallium is group 3. So what it has, it 4s2p 4p1. I mean, it has 3 valence electrons. So let me make gallium, which has 3 valence electron. Then we have silicon, which is in between. It is 4 valence electron. Then we have arsenic, which is 5, group 5. So we have 5 valence electron, right? So gallium has an extra hole. So now if you read the question properly, it says which of the following is true. So let's read one by one. So let's read option B only first. So silicon atoms acts as n-type dopants in arsenic sites. Do you really think that arsenic needs n-type dopants? It is already having an extra electron, right? Are you able to understand what I'm trying to say?
Yes, sir. Yes, sir.
Yeah. So first of all, arsenic will not require n-type dopants. So this option could not be correct. It can require p-type dopants because it requires a hole. So first of all, this silicon can give the one of the electron to this gallium. So silicon will act as a n-type dopant to gallium, not arsenic. First of all. So is there any option like that? So n-type dopant to gallium and n-type dopant to gallium. Yeah. So option A or D can be correct. So can someone please mute their mic? There is a lot of noise coming. Yeah, that is better. And now once we have established that n-type dopants in the gallium, so it will be having some hole requirement. I mean, it will be requiring a electron once it donates this to this. So arsenic or silicon can also act as a p-type dopant to arsenic because this will create a hole. So there is any option like that. Hmm. I hope you are able to understand that it will never be a n-type dopant to arsenic, right? That is why
Yeah,
option
yeah.
A is the correct answer.
First option I. Okay, okay,
Yeah,
okay. Yes, understood.
yeah, yeah. Great. So let's move forward. So again, it is very basic. try that, take 2 minutes, and then we'll move ahead. This is very busy. Oh, let me also do it. So a silicon crystal is doped with donor. So Nd is given as 10 is for 15 per centimeter cube. Assume that the Ni is this times 10 is for 10 per centimeter cube. If the same sample is additionally doped with, so now Na, we have Na as, sorry, it is 5 cross 10 is for 17. So here you see Na is greater than Nd. So this is what it makes as P type. So N will be the minority carriers now. So what is the equilibrium concentration? So this Nd will not remain as such. So the minority concentration will be Ni square by Na, which is 2.25 10 to the 20, or Na is given. Yeah, it is 5 10 to the 17. So we'll get some answer from this. 6 10 plus 3, so 2250 by 5. 5 4 5 450. J is option A. It was straightforward, I mean. So yeah, we can move ahead now. EK diagram. Okay, I need to explain what is EK diagram first. So maybe do we have some easier problems first? Yeah, so this also involves EK diagram. This is yeah. So let me quickly explain now what is EK diagram. I hope there are no doubts till now. So we'll move ahead now quickly. So we'll be like covering some of the aspect in this lecture for the EK diagram. That will require some understanding of electric field and velocities also, but yeah, let's just keep it away for now and keep it simple only. Okay, I have, yeah, that is fine. So for EK diagram, so I hope you are already about the concept of phonon scattering and photon scattering. Does anyone know what is this phonon and photon scatterings?
Sir, in case of photon scattering,
Yes.
light will be generated will be light,
Okay.
and in case of phonon, it will be heat.
Okay, it would be what? Heat.
Heat, sir, heat.
Okay, yeah, something like that, but heat will be in the form of lattice vibration. So let me quickly give a very basic.
Yes, that is vibration, sir. That
Yes,
is vibration.
yeah. So I mean, in general, when we have more than one crystal that interact with each other, we have two types of scatterings. One is photon and one is phonon. So majorly we'll be talking about phonon because that happens inside the crystal. So we have, let's say, a lot of crystal structure, as I said. So there will be, let's say, an electron goes from here to here. So there will be, first of all, due to the energy, there will be scattering. So it will move something like this and this. So there will be vibrations in the lattice that is basically responsible for this phonon scattering. And this is all being governed by quantum mechanics. I'm giving you a very basic overview. I mean, in detail, I'll be giving you in the next lecture maybe. But yeah, the basic phonon and electron interaction, basically this electron after interacting with these phonons, uh, they have some energy increase, but it has got the potential to significantly increase the momentum of the electron. So you see, there can be some energy transfer that can increase or decrease the momentum of the electron. So what I can write is, in short, is when electron interact with a phonon, there is low change in energy and there is large change in momentum. And if I talk same about photon, sorry, so in photon what we have is, whenever the electron will interact with a photon, I mean in the last lecture I talked about the Planck's constant, sorry, the photoelectric effect. So once we have a certain photon interacting with the electron, there is a large change in energy. Basically the electron comes out of that metal. So we have large change in energy and low change in momentum. This is very basic. I mean, this all comes from a lot of concepts, but due to the constraint of the time, I'm just giving you a very basic idea. So once we have established that for phonon we have a large change in the momentum, and for photon we have a large change in energy, here comes a concept. Yes, someone has raised their hand. Yes. Any doubt?
Sir,
Yes, yes.
sir, actually, sir, these, if possible, sir, this class will be conducted from 4 to 6, sir. Because, sir, it will be, sir, means I have walking in the outside, so it will create some problem, sir.
Okay. See, we don't have a control on the time. So what you can do, maybe you can see the update, lecture recording on the YouTube. It will be available. But see, it is
Okay, okay,
fixed.
okay.
Yeah, it is fixed from 6 to 8. I cannot change that. It is
Sir,
governed by
sir,
the.
is there link is available in YouTube?
Yes, yes. So there is a drive link that might have been shared with you already. So all the videos are available there.
Okay, okay. Thank you, sir. Thank you.
Yeah, yeah, no problem. Yeah, so what I was saying, yeah, due to this thing, so there is a thing called as effective mass. So for an electron, now what we know is energy is, sorry, what I was telling, effective mass. So for an electron, what we have is energy is half mv square, right? So I'm writing something as star. So to denote it as effective mass, so I'll tell you why star. Again, momentum is mv, we already know that, and half 2 mn star if we write in terms of potential, sorry, momentum, so energy is something like this. So what I can write is E is P square by 2 mn star, and this momentum is h cross k. This is the basic relation where k is a wave number. So I can write h cross square by 2 mn star k square, yeah, square. So E is a function of k square with some constant, right? So this is how EK diagrams comes into the picture. So it is a parabola. This is E, this is k, and the slope will be governed by the effective mass. So if we have a very high effective mass, the slope will be lower. I mean, this is quite straightforward. So what we can say is the electron in a crystal are not completely free, but instead interact with the periodic potential of the lattice. So due to this, what happens is the wave particle motion of the electron cannot be expressed to be the same as for the electrons in free space. So applying all these equation, what we have is we need to use some altered value of the particle mass, which is not exactly equals to the mass which is in vacuum. So that is why we take effective mass. It is what we call as effective mass, that is considering all the phenomena that are happening in the surrounding. The mass of the electron after considering all that is called as effective mass. And in doing that, so what I can say is, sorry, what we can say is, if I like double differentiate it, so d by dk will be h square by 2, no, 2 will go away, mn star k, and d2e by dk2 will be h cross by mn star, right? So what I can say is this effective mass is nothing but h cross square by d2e by dk2. So what we can now clearly see that by effective mass, that higher the slope of the double derivative, smaller will be the effective mass. I mean, this is just a general relation which people teach. And if I now apply some basic concept, so F is m into A, which is the Newton's second law. So let's write mn into A, and it is also equals to charge time electric field. I mean, this I'll talk in detail in the subsequent classes. So what I can write is A is QE times mn star, right? And A is basically nothing but change in velocity. dv by dt is QE times QE by mn star. Sorry, it went away. नहीं. Yeah, so what I can do is I integrate, let's say, to a term called as drift velocity. So I'll explain this. I mean, just wait. And here what we can say is, let's say some collision time, which is tau. It is QE by m star, right? Dt. So if we try to calculate, so here it comes Vd, and here it comes QTC by mn star, and E is also remaining. So this is how our drift relation comes, which is Vd equals to mu E. This is what you have seen in a lot of books. So this mobility is nothing but Q tau by m star. So now here you see, higher the effective mass, lower will be the mobility. I mean, if the particle has more weight, it will try. I mean, in general, if we talk about humans, if we have a higher weight, it is difficult to move. But if we have a lesser weight, it is very easy to move. So the particles with a higher effective mass have low mobility, and the particles with a lower effective mass have higher mobility. So that is why in general the electrons have a higher mobility than that of holes. Make sense, everyone?
Yep, yep.
Okay.
I have one doubt. What
Yes.
does differentiation of E, like energy with respect to wave number, actually represent?
Energy with respect to, sorry.
I mean, yeah, yeah. It's d E by dk.
Yeah, yeah. Okay, okay.
Like
So
if you quantify it as a physical quantity, like do we derive anything from that?
no. So basically, why I did the double differentiation is to just show you that if we have a higher differentiation value, so this effective mass is lower. So basically, if we have a very low effective mass, let's say, so we will have a very high slope. I mean, very high means something like this. But if we have a very high effective mass, then we have a very low value of slope. So the EK diagram will be flatter. And this is the EK diagram when we have a very low value of effective mass. So I mean, in general, we see these EK diagrams. So just to make you familiarize with that, that is why I wrote this thing.
Okay, okay, I got it. Like it is representing the slope, right?
Yes,
Yeah.
yes, yes, yes.
Yep, yeah, got it. Got it.
Yeah, great. Yeah, so I mean, now we have a problem. So in EK diagram, as it says, each portion of the curve represent the allowed band energy level. So as I said already, so I mean, if we make in general, let's say I'm making it for direct band gap only. Let's say this is, sorry, this is K, and this is energy. So this is the below, so this is conduction band, this is the top of, so this is something like this. So each of the points represents the band energy. So this is correct. The curve has a zero slope at the top and bottom. Is it zero? Anyone? This is basic maths, I mean. Can you tell if the slope is zero here?
Top, top and bottom, as in
Top of conduction and bottom of valence. Oh, sorry, bottom of conduction and top of valence. The red points.
yes, slope is zero.
Yeah. Why? Because we have a local minima and maxima. The slope can only be zero if the differentiation is zero, right?
Yes, yes.
Yeah. So it is also correct. The curves are parabolic near the top and top of valence band, so it is also correct. The curves are parabolic near the bottom of the conduction band, so it is also correct. So all the options are correct. I mean, this is just to give you a very basic idea of the EK diagram. So yeah, any doubts till now?
Why do we get that curvature?
Which curvature? Yes.
That is because of that wave number, what you said, right?
Yeah. I mean, oh, the
Uh,
nature is why it is like that because of this. I mean, this is basic physics. Half mv
okay,
square, and this v is p and p is hk. So this is basic physics. I mean, there's
okay,
no
okay.
problem.
I'll look at. I
Yeah,
have
yeah,
missed that. Okay, I'll. Thank you.
yeah. So E is directly proportional to k square, parabolic. Yeah. So I mean, yeah, this is most of the part of EK diagram, and the effective mass also I've covered in that. So that is, I mean, all the topics, I guess. Let's see some numericals if we can. Yeah. So band shift effective mass, doping, reciprocal. Yeah, everything is covered mostly. Let's see if I have some numericals or This is all generic. X-ray, X-ray. Yeah. So we have one more concept. I mean, this will require some of the knowledge of quantum mechanics. Let's do that also. I mean, then we can stop the lecture. So, as we already said, that electron can behave both like a wave and a particle, if we talk in terms of semiconductor physics. So, all of that is a probability, right? So, it all comes down to this quantum mechanics, and we do have a term known as wave function to determine whether the electron exists at a particular level or not. So, it is all probability. There is no definite way to govern whether the electron is there or not. So, this is what we govern by the wave function. So electron behave like a particle with a wave character, that is wave particle nature, and let's say we want to model it. So this is the thing that we'll be modeling, and it contains all the information such as energy, momentum, etc. And it has certain properties. So wave function, which is denoted by psi, it must be a solution of Schrodinger equation. So anyone know what is Schrodinger equation? Anyone? Schrodinger equation, it is class 11, right?
Man, it is like somewhere like we say the electron state is in both the state somewhat.
Yeah, so okay.
Um,
Yeah, no problem. So I mean, we know the total energy of electron could be kinetic plus potential, which is the total energy, right? So kinetic, if I write very basic, it is p square by 2m. Potential, let's say, is something constant as v. So in quantum mechanics, what we write in general is that we use the operator, as I said. So there is a probability, right? So we write something like minus h square, h bar square by 2m times d2 psi by dx2 plus v psi is e psi. So this is what Schrodinger equation is, and this is time independent. I'm not writing a time dependent term because that is not needed. That will make it complex also. So this is a time independent equation, and this is what we solve to consider some or lot of the different cases such as infinite potential well. Then there is a case called as finite potential well. So we'll be maybe at least seeing the derivation of infinite potential well because that is a problem. So for a particle in 1D infinite potential well, the wave function is this, where k is this, calculate A. Yeah, so let's try to do it quickly. So I'm talking about infinite potential well right now. So what it means is we have a well, let's say it is 0 here and L here, and everywhere the potential is infinite except this well, and it is 0 in the well. Makes sense to everyone? This is an infinite potential well. Why I'm calling it an infinite potential well? It makes sense, right?
Usually it is a bell curvature.
Sorry?
It will be bell curvature.
No, 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 no. It is perfectly square. I mean, there is a well from 0 to L, which is having a 0. So the bell curvature is a wave function. I mean, that is, I guess, what you're trying to say. So this is for n
Like
equals to
we
1.
say that highest energies at the well, that the same concept.
Say it again. Highest what?
When I studied Schrodinger equation, how I remember is we have the maximum energy at the bottom, and as you move away from the like towards the upward, you get some minimum energy.
Uh,
Okay,
you're
maybe
saying
wrong.
something like this?
No, it is the same curvature, like
Hmm.
the uh, whichever you have drawn,
Hmm.
but like somewhere I've seen the bell curvature. Little different concept, I feel.
Something like this?
Yeah.
Okay, it is not like that. I mean, if you can share the documents, I mean, I'll be.
I'll check. I'll
Yeah,
check.
sure, sure, yeah.
Yes,
So
thank
what I'm trying to say is V0 between x0 to L and v is infinity elsewhere. So this is what we'll do to solve the Schrodinger equation. So v0 when x is between 0 to L, sorry, x is between 0 to L. So I can write minus s square by 2m d2 psi by dx 2 plus v, which is 0, is equals to e psi. So this is a direct solvable Schrodinger equation, I mean double differential equation. So I can write this as e by, okay, 2m will come up, then h bar will go down, and this is psi. Yeah, so what, let's denote this as maybe k square, which is this, or we can write k as under root 2me by, I mean this is a general term only, so to simplify I'm writing this, whatever this thing is, k square psi. I hope this is clear. So so if you just simplify it, or if you just double integrate it, it will come out to be a sine kx plus b cos kx. So this is the solution to this. I mean, you just need to integrate it twice, so you will get this solution. This is quite basic. So now what we know is at x equals to 0, we have a psi which is 0, and at x equals to L, we have a psi as, sorry, at psi, not psi. So first let's do this. So psi at 0 is 0, which is a into sine 0 is 0 plus b into cos 0 is 1. So b comes out to be 0. So I'm doing it quickly and like considering that you already know the solution to this, right? Everyone, are you already aware? Otherwise we can do it like in a slow pace later. Uh,
Yeah, it's just the equation.
yeah. So similarly at x equals to L, we have psi as 0. So if you do that, you'll get the value of k as n pi by L. That is what is given in the question. And from here you will get a sine n pi x by L. Yeah. And then by using the normalization factor, which is at 0 to L, so since this is a probability, so the total probability will always be equals to 1. So if you just keep it, I mean if you integrate it and all, so the a will come out to be root 2 by L, and the final wave function will look something like this, root 2 by L sine n pi x by L. I'll give more details in the further classes, but I mean just to give you the idea. So this is how the solution of the wave function looks like for a Schrodinger infinite potential well. So if you take n as 1, so the solution of the wave function is like this. So this is n equals to 1. So if you take 2, so it is like this. If we take 3, so it will be something like this, and so on. So this is what the question has asked. So the value of a is root 2 by L. We'll cover these in the subsequent classes, but yeah, just to give you a very basic idea, I need to do it very quickly. Is it clear to everyone? Yeah. So maybe we can stop for now, because this concept of drift velocity and mobility, this will take some continuation. So we can do it, like we can start from that in the subsequent class. But I have already covered the concept of the topics that are already present in this week too. If you have any further doubts, you can ask quickly. Otherwise, we can dismiss the session and we can meet next week the same time.
Yeah, sure. Yeah, thank you, Anant.
Okay, yeah. Great then.
Thanks.
So we'll meet same time at the next week. Till then, bye bye
Okay.
everyone.
Yep. Thank you.
Thank you, sir.